Okay, so the notes are going to pick up with example 16. That's where we were. We're talking about systems. Find the acceleration and the tension for the picture on the right. You've got mass 1, which is 3.1 kilograms, and mass 2, which is 4.4 kilograms. So first tells me to find the acceleration. So what I need to do is I need to look at this. For the acceleration, I'm going to look at it as a system since these two are attached. So if we look at the system here, really the only two things we have going are we have mass times gravity of the first mass, and then we have mass times gravity of the second mass. Well, this guy's going downwards and this guy is technically accelerating upwards. So if we do the sum of forces, which is the mass total times acceleration, we get mass 2 times gravity minus mass 1 times gravity, okay? So let's fill this all in. So our acceleration is going to end up equaling mass 2g minus mass 1g divided by the total mass. So mass 2 is 4.4 times 10. We've got 3.1 times 10. Oops, there should be a minus between those, divided by 4.4 plus 3.1. We end up with an acceleration of, what do we end up with? An acceleration of about 1.73 meters per second squared. Now, to find the force of tension, we just need to look at one of them. So the force of tension, if we look at the free body diagram for mass 1, let's say. So for mass 1, we have m sub 1g going down. We have the force of tension going up. We know this thing is accelerating that way, which means my sum of forces, which is equal to mass 1 times A, is equal to the force of tension minus mass 1 times g. So force of tension, if I figure this out, force of tension is simply going to be mass 1a plus mass 1g, which makes sense. So if I pull mass 1 out, I get 3.1 times the acceleration, which is 1.73, plus gravity, which is 10. So we get approximately 36.4 newtons when we do all our math, okay? So now, and feel free to slow this down and back it up if you need to. Anytime I'm finding the acceleration, though, I'm going to be looking at this from the standpoint of the entire system and just what's working on the system. I'm going to treat tension in these cases as an internal Newton's third law, action-reaction force, and I'm going to leave it out, okay? So now, just to make sure everybody understands what I'm doing, if we have a 3.5 kilogram block on the tabletop, release from rest, coefficient of friction, so we have friction. So we know we have force of tension going this way. We have the force of friction going this way. We have force of gravity for block 1 this way. We have the normal force on 1 going this way. This way we have the force of tension again, and we have force of gravity on 2 going that way, okay? So we need this entire system to find the acceleration. It's allowed to move freely. So the first thing we need to figure out is if it's accelerating at all. So let's look at this guy. If it's accelerating, it's going to have to be accelerating downwards. If we end up with an acceleration that's positive for making that downwards, that would make it this way. If we end up with a negative one, we know it had to be going the other direction, which I can't do. So let's find the acceleration, which means we are simply going to look at the entire system without the force of tension. So we're going to be looking at this, like this. So my external forces on this guy are simply going to be the force of friction this way and the force of gravity that way. So for acceleration, we know the sum of forces is going to be equal to the total mass times the acceleration of the system equal to the force of gravity 2 minus the force of friction on 1. Okay, so that's the external forces here. Force of friction is negative because it's slowing it down. It's going opposite the acceleration there. So the total mass would be 3.5 plus 2.8 times the acceleration equals the force of gravity on 2, which would be 2.8 times 10, minus the force of friction, which is going to be mu times the force of gravity on 1. So 3.5 plus 2.8 is 6.3. So we have 6.3a equals 28 minus force of gravity on 1, of course, is going to be the normal force. Well, this really should have been the normal force, shouldn't it? But that is gravity if you look at your picture. These two guys are equal. So force of gravity on 1 would be 3.5 times 10. So we have 0.4 times 3.5 times 10. So we have 6.3a equals 28 minus 35 times 0.4. Looking at that on my calculator. So we end up with an acceleration that is approximately 2.22 meters per second squared. Okay, so now that we know that, we're trying to find the tension, we can just do one of these. I'm going to choose to pick this guy because it's the easiest. So for part B, we're going to do the sum of forces in the y direction is equal to mass of 2 times the acceleration of the system, which is going to be F sub G2 minus the force of tension. So when I end up working this out, I get the force of tension, which moves to this side, is the force of gravity of 2 minus m sub 2a. Force of gravity 2 is the mass 2.8 times the gravity, which is 10, minus mass 2, which is 2.8 times that acceleration of 2.22. Work that all out, we get 28 minus whatever, and we end up with a, let's see, .78 newtons. So that's my force of tension, and sure enough, that works out for both of those. All right, so if you see what I'm doing, I'm using the system, idea of system for only the external forces for figuring out the acceleration, and then I use an individual block to find the tension. Hopefully that makes sense. All right, frictionless mass, we're gonna look at these guys, find the acceleration of the objects. This is gonna be easy enough. So we're gonna do this again. So we're gonna treat this, we're gonna look first at what are all of my things. I've got force of tension this way, I've got mass 1 times gravity this way, I've got normal force this way, and frictionless surface, so that's it. So we have force of tension this way, and we've got mass 2 times gravity this way. So for the acceleration, I'm going to treat it like a system, and only external forces. Well, the only external force, guys, is that one right there. So I know the sum of forces. This is going to be acceleration downward, acceleration this way. So the force, sum of forces, is going to be the mass total times the acceleration of the system is only going to be equal to mass 2 times g. So mass total is mass 1 plus mass 2. That's equal to mass 2 times g times the acceleration. So if we divide, we end up with mass 2g divided by m1 plus m2. And sure enough, if you look, see it, but you see how that's done. Now for B, if we're finding the tension on the string, I'm just going to use the tension on the string. I'm going to actually use this guy this time because that's super simple. So the sum of forces in the x direction for that block is going to be mass 1 times the acceleration. Mass 1 times the acceleration has to be equal to just the force of tension in this case. So I've got mass 1 times my acceleration, which I just found, which was mass 2g divided by mass 1 plus mass 2. I'm simply going to take this and plug it in right there. And that's equal to the force of tension, which, if you work it out, mass 1, mass 2, g over mass 1 plus mass 2. And look, sure enough, that's what that is. So you can see this idea of doing external forces for the acceleration and internal one block for the tension. All right, so now this one gets a little more complicated. Which way do the blocks accelerate and what is that acceleration? So we can just take this and ask ourselves, which way do we think this thing is going to go? I'm going to tell you that I think it's going to go this way, which means that will go that way. If I am wrong, then my acceleration will end up negative, and I'll know it's going the other direction, okay? So let's look at this guy. I don't know which way it's going, so I'm going to pick it out, but I think it's going to go the steeper direction. So now we have to come up with our free body diagrams for these. So these do really require kind of a free body diagram thing. We're still going to use the system for acceleration, but my free body diagram for this guy is going to be, we'll call this mass 1. Mass 1 times gravity this way, but this is at an angle. So we're going this way. So really what I've got is I've got m1g sine 30, and I've got m1g cosine 30 this way. I've got the force of tension this way. Frictionless plane, so I don't have to worry about that. So I have my normal force for 1 this way. Now, same thing goes for this other guy. This guy is going to have a normal force 2 this way, force of tension this way, and then it's going to have mass 2 times gravity this way, but we're going to have it going, there's my theta there, this way and this way. So this guy is going to be mass 2 gravity times the sine of 53.1 degrees. And this is going to be mass 2 gravity cosine 53.1 degrees. Okay, now this is going to become important because if we're finding the acceleration, we can treat all of this as sort of like it's on a flat system. So what we have is we've got force of tension this way, the other one, force of tension this way, backwards going that way. We've got m2g sine 53.1 degrees, okay? And backwards this way we have m1g sine 30. So if we treat this, so force of tension is this way. So if we treat this just externally, like to find these two equal and opposite, we think the acceleration is this way and this way. Now that we're looking at it sideways, I basically flattened it out. All right, so the sum of forces, which is going to be the total mass of the system times the acceleration of the system, is going to be that m2 g sine 53.1 degrees minus m1g sine 30 degrees. So acceleration is going to be m2, which is 100. So we have, 50. So we have 50 times 10 times the sine of 53.1 degrees minus 100 times 10 times the sine of 30, all divided by 50 plus 100 is 150. We end up with an acceleration of 0.66 meters per second squared, and it ended up as positive, which means that I did guess correctly, and it is actually going to the left. It is going, hang on, did I guess correctly? Hang on, let me double check my math here. 500, 53.1 minus 1,000, sine 30, negative. It's negative. It's negative. I've got it going to the right, but it's negative, which means that the acceleration is actually 0.66 meters per second squared to the left, because I had it going right, and so it was opposite, so it's going to the left. So this thing is going to the left, 0.66 meters. See, because I had it going as right is positive, but in my pick. But it ended up negative, which means that it was actually left. All right, so make sure everybody understands that. That's the system approach. For part B, tension in the rope, we're just going to use one block. Okay, so the sum of the forces, I'm going to use for this guy, I'm going to use this block right here, which means I'm going to use this force and the force of tension. So the mass of 1 times the acceleration. And now we know the actual acceleration is going this way. So if we're going to use it as positive, we know that it's going down that hill. So that is m1g sine 30 degrees. So this is positive, which means that's negative, minus the force of tension. So m1 is 100 times 0.66 equals 100 times 10 times the sine of 30 degrees minus f sub t. So f sub t ends up equaling about 433.3 newtons when you do the math. Okay? All right. Hopefully those are all making sense to you. All right, example 20, systems. So now we want to know in part A, we want to know 2 crates lie on a horizontal surface. Crate A has a mass m, crate B has a mass b. Coefficient is mu sub k, so we know they're pulled to the right with a constant velocity, which means my acceleration is equal to 0. All right. Constant velocity by a force of F. Find the following answers in terms, okay, the magnitude of F. All right, so the magnitude of F is going to be, well, we got to see what's going on. So what do we know is going on here is we know if we look at this internally, that, or externally, so we're going to look at this for part A, I'm going to look at it as a system. So if I do the forces here, I've got mass A times gravity. I have the force normal of A. I have force of tension this way, and I have force of friction this way. For B, I have the mass of B times gravity. I have the force normal of B, they're not the same. I have the force of tension, which is the same. I have the frictional force going this, or the force going this way, but because the force is going that way, I also have force of friction of B. Okay? So now, what is going on here? Now, if both crates are the same, what do we know? Well, we can't do an internal-external force thing here. We've just got to do each of them. We're going to do everything, okay? Now, how are we going to do everything? Well, what's working on the system and what zeroes out? Well, I can tell you right away what zeroes out is this and this. Those are equal and opposite. Everything else is not. And we know the whole thing is going that way with an acceleration of 0. So, sum of forces in the x direction is going to be 0. That 0 is equal to big F minus the force of friction on B minus the force of friction on A. Okay? I just didn't even include tension because they're equal and opposite in this particular case. I know that this is a positive force, this is a negative force, and this is also a negative force. So now, why did I list those separately? Because they're not the same mass, the crates aren't the same mass, therefore the force of friction can't be the same mass. So what we're going to do is we're going to do this is F equals mu times normal force is in A is m sub A g, and the normal force on B is m sub B g. So this is mu m sub B g. This is minus, and this is going to be mu times sub k, use correct subscripts, m sub A g. And this is all equal to 0. Okay, so the force is equal to, bring these both to the other side, and we get mu sub k is the same for both of them, gravity is the same for both of them, and it ends up being m sub b, I don't know why I just did b there, m sub b plus m sub a. Signs change when they both go over, become positive. So there's my force. So that's A, magnitude of force. B is the tension on the rope. Okay, tension on the rope, I just need to use one of the boxes. So I'm going to use this box because there's fewer things going on. Okay, so the tension on the rope for this guy is going to be the sum of forces in the x direction, which is still 0 since it is going a constant velocity, right? Which means that these two forces have to be the same. So the force of tension has to be equal to the force of friction on A, which is equal to mu sub k times m sub a g. So there's my force of tension, equal and opposite. All right. I think this is our last, we only a couple more systems examples, and then we'll be done. And if you're good, you're good. But knowing how to work these as a system versus to find the acceleration is always a lot easier. All right, push a 1 kilogram food tray with 9 newtons of force. Tray is pushed on a 0.5 kilogram milk carton. Tray and carton on a greasy surface, so no friction. Find the acceleration of the tray and milk carton, as well as the force the tray exerts on the carton. So acceleration can be treated as a system. So if we treat this whole thing as a system, what do we have going on? Well, let's look. We have, if I'm looking at this guy right here, if we do the free body diagram, we've got force of gravity of 1 downwards, force normal of 1 upwards. It has a tray. It's got a force being, it's pushing against it's got an applied force, and the milk is pushing back against it. Okay? This guy has the tray pushing against it. It is backwards. Let's see, force of gravity of 0.5 and force normal 0.5. So force of the tray is one way, force of the milk is the other way. We know that both of those are equal and opposite, aren't they? So this guy kind of cancels this guy out. So the only thing we have acting is this guy right here, out of the system. That's the external force, which makes sense if you think about it, since it's the push. All right, so if we do the sum of forces in the x direction for the entire system, we get the mass of the system times the acceleration equals the only thing that's there, which is that 9 newtons. So the mass total is 1.5 times the acceleration equals 9. So the acceleration is equal to 6 meters per second squared. That's the easiest way to do these for acceleration, is to treat it like a system if you can. So now it wants to know the force the tray exerts on the carton. Okay, so now I'm just going to deal with one of the blocks. So if I deal with one of the blocks, then I can very easily just look at, let's say, this one. Doesn't matter which one you pick. So we're doing the 1 kilogram. So for part B, we're going to do the sum of the forces is equal to the mass of the 1 times the acceleration. And we're pretty sure it's accelerating that way, which means that it's the force applied minus the force of the milk back on that guy. Okay? So that seems kind of complicated. Blech, I don't want to do that one. This one's only got 1 force on it. Why wouldn't I do that one? Force of the tray. Okay. So sum of forces is equal to mass 2 times acceleration, which is just equal to the force of the tray. Okay, so the force of the tray is equal to the mass of 2, which is 0.5, times the acceleration, which is 6. Oh yeah, this is way easier. Force of tray is 3 newtons. So you can pick and choose if you choose, I mean, we could have worked it the other way. We could have said 9. We could have said this was 9 minus the force on the tray, or force of the milk, is equal to mass 1, which is 1 times 6. So it still would have ended up as 3, but this one was faster. Okay. 3 blocks being pushed. Ooh, this one's cool because we can still treat it just like an entire system. Because all of these, this pushes on this and this pushes back, this pushes on this and this pushes back, are all action-reaction pairs. They go away. This is the only external force right here. So the sum of forces to find, which is the mass total times the acceleration, is for this guy just equal to that 24 newtons. So the total mass is 3, 2, 1. You've got 6A equals 24. Well, A is then equal to 4 meters per second squared. Super easy. Now, you don't have to worry about all those action-reaction pairs. Now, the force that the 2 kilogram block exerts on the 1 kilogram block, now we got to look at all of these forces, okay? So now we've got to actually do free body diagrams. 2 kilogram on the 1 kilogram. So the 2 kilogram block is here. Let's do the 3 first. So the 3 kilogram block has a 24 this way and has the force of 2 onto 3, okay? It has 3G this way, right? Which is 30. So we'll just call this 30 newtons. And this way, we don't worry about the frictionless plane. So this is the normal force, which is 30 newtons. Now we got the free body diagram for block 2. We got 20 this way. And normal force, which is 20 newtons this way. We now have the force of 1 onto 2, and then we have the force of 3 onto 2 this way, okay? Notice the 24 doesn't apply to it. The 24 only applies to the block it actually pushes, is being pushed. Last block, we have 1 times 10, so we have force of gravity, which is 10 newtons this way. We have the normal force for this guy, which is 10 newtons this way. We now have the force of nothing going that direction. But we do have the force of 2 onto 1 pushing this way. All right, so what do I need to know? I need to know 2 on the easiest one, which is I want to know 1 onto 2, and 2 onto 1 is the same, so I'm going to pick this block right here. So the sum of forces, which is the mass of 1 times the acceleration of the system, is just equal to the force of 2 on 1 at this point, because it's the only force there. So the mass of 1 is 1. The acceleration was 4. So the force of 2 on 1 is just equal to 4 newtons. Super simple when you look at it like that. System is for this guy. All right. 23, still on systems. And then we're going to jump into the calculus portion here. A 6 kilogram block is in contact with a 4 kilogram block on a frictionless surface. All right. 6 kilogram block is being pushed by 20 Newton force. Boy, I hope you know how to do this. First thing we're going to do is find the acceleration. I'm going to find the acceleration by looking at the whole thing as a system. So by now, you should know that the acceleration is going to be the total force, which is 20, external force, which is 20, divided by the total mass, which is 10. So we know this thing is going 2 meters per second squared. That makes it super easy, okay? 6 on the 4 means I'm just going to look at this guy. This is going to be the force of 6 onto 4, and that's the only force on that block. So the sum of forces in the x direction, which is going to be that 4 times the acceleration, is going to be equal to just F of 6 onto 4. So 4 times 2 is equal to 8 newtons of force. Okay, and that is the force of 6 on 4. Hopefully these difficult systems problems look really much easier when you look at it system-wide for the acceleration. And then look at the block to find other things that has the least number of forces acting on it. All right, calculus. Now, we got to look at calculus here. A 2 kilogram object following a position described by the equation. What's the net force acting on the object at a time of 1 second? Well, to know that, we've got to find the acceleration, don't we? So we know the velocity with respect to time is going to be dx dt, which is going to be 4t minus 3 times 3 is 9, t squared. We also then know the acceleration with respect to t is going to be dv dt, which is going to be 4 minus 18t. Okay, so 4 minus 18t, the acceleration at 1 second is going to be 4 minus 18 times 1, which is negative 14 meters per second squared. So the net force acting on that at 1 second, if you've got a 2 kilogram object, the net force is just going to be the mass times the acceleration. So you've got 2 times negative 14, which is going to be negative 28 newtons. So that's part A. Now for part B, the net force acting on the object is positive from 0 until a time of what? Okay, well, positive until it gets to 0. So we need to know when is the acceleration equal to 0. So when is acceleration equal to 0? So when is 4 minus 18t equal to 0? Which makes negative 18t equals negative 4. So time is going to be 0.22 seconds. So from a time of 0 to 0.22 seconds, the acceleration is positive. So net force is positive. Okay? All right. Easy calculus. So now we've got an object moving along with the speed. What's the initial velocity of the mass? Well, let's look. We just need to know the velocity at time 0, don't we? V naught would be equal to V at 0. So what is the initial velocity of the mass? That would be equal to C plus B times 0 cubed. So it's C. Net force acting on the mass at time t. Okay. Net force is going to be what? Mass times acceleration. So the first thing we need to know is the acceleration. The acceleration of t is equal to dv dt. So dv dt is going to be 3b t squared. So the acceleration at t is going to be 3b big T squared. Okay, so the sum of the forces then, if we take that and plug it in, the sum of the forces is just going to be 3mbt squared. We'll just multiply it by m. Calculus is easy. Uniform circular motion now. Uniform circular motion is, we are looking at, what do we know? We know uniform circular motion is the motion of an object in a circle with a constant uniform speed. That means a uniform speed, it's not constant. Uniform circular motion is not uniform unless it's at a constant speed. If the speed varies, then we're in a whole different realm, all right? So what we need to know, and at a constant radius, it can't be going in or out. So things we need to know is that uniform circular motion, of course, we've got an average speed, which is distance over time. Well, the distance, of course, in a circle is its circumference. So the average speed is going to be 2 pi r over t, the time. Big T is the period, how long it takes to make a full revolution. So the average speed is going to be the circumference of the circle divided by the period. Okay? And I want you to look at this, though. The further out it is, the bigger the radius is, the higher the speed it is for the same amount of time. Think about it. You've got a bigger radius, you have a bigger circle to take in the same amount of time, so it must be going faster. All right. So now, definitions. Centripetal means towards the center. So centripetal acceleration is always towards the center of the circle, as you can see from the red arrows right there. In order for an object to be in uniform circular motion, the force needs to be acting on it, and the force is always in the direction of the acceleration, so the force is always towards the center of the circle in uniform circular motion. Force centripetal also is, so that's why it's called center seeking, okay? Centripetal force is not a real force, it is an imaginary force, and you do not put it on a free body diagram. So it is never, force centripetal right here is never on an FBD. Never, never, never. Tangential velocity, we know if the acceleration is interior, if we were to snap the string that it was on, if it were on a string, it would fly out tangentially. So these are the things you need to know. You need to know centripetal force, F sub C, is equal to mv squared over r. You need to know that centripetal acceleration is v squared over r, because if we take F sub C equals to, because this would be equal to m a sub c, so the m goes away, and that's where this comes from. And then we know that the velocity, tangential velocity, is going to be equal to the distance it covers over the period of time, and that would be the circumference divided by the period. So that's our tangential velocity. Okay, that's our average speed. Right, so now let's look at what we've got going here in terms of examples. We're going to start easy. We've got a car, if it's going around a corner that has a radius, it's circular, so the radius right here. Coefficient of static friction between the tires and the road. Here's the thing you've got to know. If we're doing a free body diagram of this guy right here, this guy wants to go, if you were to keep going, it would want to fly this way, which means that the force of friction is inner. So the force of friction is acting this way. We know that it has a gravitational force downward and a normal force upwards. So if we were to do the sum of forces, in this case centripetal, because it's going around a corner, that is ma sub c. So ma sub c in this case is equal to that force of friction. Okay, so what we know is ma sub c is equal to what? Mv squared over r, because we know what's the greatest speed, so we're looking for the velocity without skidding. We want them to be equal because without skidding means they are the same, is equal to mu times the normal force, which in this case is mg. All right, m goes away, don't care about the mass. All right. Static friction, not kinetic friction between tires and a road, because it's not sliding, that's the whole point. So we want to know v squared is equal to mu sub s g r, right? And then we're going to take the square root of that. So the velocity, the max velocity, v max, is going to be equal to the square root of 0.82 times gravity, which is 10, times the radius of the road, which was 45 meters. Okay, so Vmax is 19.2 meters per second. Okay, simple enough. Looking at the same one, it says figure out what, we just did this. Maximum speed without sliding. Well, this is the exact same equation, isn't it? We know that friction is the only thing acting this way, so that we know the sum of forces is going to be equal to ma centripetal. Well, ma centripetal is equal in this case to just the force of friction. So we have mv squared over r, which is equal to 0.82 times 10 to the minus 9 mu mg. U sub s mg. M goes away again. So V max is going to be equal to mu sub s gr square root of, because we had to take the square root of both sides. Same problem all over again. All right, tension in the cord at the bottom of the ball's motion. So if this thing is vertically, this is going to change things a little bit, guys. We've got to look at this from the standpoint of what would it be doing if it were vertical. All right, tension of the cord at the bottom of the ball's motion. The bottom of the ball's motion is going to be here. If the bottom of the ball's motion is there, then we have mass times gravity this way. We have tension acting upwards. So they are acting opposite each other. All right. So for part A, we'll put part A up here. If we have the sum of forces centripetal, this is going to be MA centripetal. Well, MA centripetal in this case is going to be acting towards the center as centripetal acceleration. So that is going to be the force of tension minus mg. So we have what? Tension in the cord, circular speed. So we have mv squared over r equaling the force of tension minus mg. So the force of tension is going to be equal to mv squared over r plus mg. Makes sense, doesn't it? More tension at the bottom than at the top. It's going to pull tighter at the bottom. So we have I'm not even going to plug in. You can plug all the values in. If we plug all the values in there, we do end up with 24.32. So let's look at B. Tension in the cord at the top of the ball's motion. Now at the top of the motion, I'm going to do that in a different color. I'll do that in blue. So at the top of the motion, however, mg and the force of tension are both acting in the same direction. So there's going to be less force on that. So if we do the sum of forces centripetal here, ma sub c this time is both going to be mg plus the force of tension. So the force of tension, guys, is going to equal ma sub c minus mg. So there's more slack on the cord at the top because gravity's pulling it down. All right, so it makes sense if you think about it. So the force of tension, you guys can plug in there as well. You will get 1.72. And then it says, what's the tension of the cord when it's on the right side? Okay, so we'll do that in an opposite color. We'll do that in green. So if it's on the opposite side right here, what do we have going on? We have the force of tension only. Mass times gravity is this way. Okay, so for part C, all we have is the sum of forces, centripetal, which is mass times centripetal acceleration, is just equal to F sub T. In that case, it's even lighter. All right, so now in all of these, it's super simple. Now, of course, we would have to change, y'all know, in both of these, we would have to go with mv squared over r, mg, and of course in this one, we would have to go mv squared over r. Okay, so easy peasy. Plug your numbers in. Did I skip one? Yeah, I did. All right, these guys, y'all will know, draw the free body diagram of the mass. All right, they've given me a red dot over here. What are the free body diagram of this mass? Well, we have force of tension going this way, and we have mg going that way. That's my free body diagram for this guy. That's it. But we do know that there is some acceleration happening here towards the center of the circle. The acceleration happening towards the center of the circle is going to be centripetal acceleration, that direction, isn't it? All right, constant speed tells me that. So we did A. Here's A. Now let's do B. What's the tension in the string? Well, B, the tension in the string is only going to be the portion of the tension that is towards the center of the circle, because that's what we know. Well, or at least we can find that piece of it. So if we take this guy and we draw it here, And here, we've got this theta up here. That tells me the component here is going to be F sub t sine theta. That's that portion, isn't it? So F sub t sine theta is going to be acting towards the center of the circle. So sum of forces for B, centripetal, is going to be mass times centripetal acceleration. Well, that mass times centripetal acceleration is just F sub t sine theta, okay? Which means that this guy is going to be what? Oh, I did it the hard way. What's the speed of the ball? Because I can't do it with this. So let's call this C, and we'll get back to this in a minute. Let's go to B, because really, wouldn't it be easier to use this guy versus this guy to get the tension in the string? Because this guy is F sub t cosine theta. I'm going to use that instead. So for B, I'm going to say the sum of forces in the y direction, which is 0, quite frankly, because it's not moving up or down, is going to be equal to F sub t cosine theta minus mg. So F sub t cosine theta is equal to mg. So F sub t is equal to mg divided by cosine of theta, which is going to be approximately 14.94 newtons. Okay, well that makes the third part easier. What's the speed of the ball? Well, this is going to be mv squared over r equals F sub t sine theta, plugging everything in. We're going to get the speed of the ball. V squared is equal to r F sub t sine theta divided by m. Take the square root of the whole thing. So let's figure out what that is. R is going to be the radius is what? Ooh, we don't know what the radius is. Do we? You know what? I got to find the radius of this string. I know the length of the string is 0.8. So the radius of this circle, which I need right here, is going to be 0.8 times the sine of 14 degrees. So I got to plug that in. So I have 0.8 sine 14 degrees times the tension, 14.94, times the sine of 14 degrees again, divided by the mass. Mass is 1.45. Square root of the whole thing. Should get 0.69 meters per second. Okay, I'm gonna double check that. 0.8 times sine 14 times 14.94 times the sine 14. Yep, 0.69. Okay, so that was C. All right, almost done here. Example 29. Got three more examples here. So how do we get this? All right, it says conical pendulum with a thin wire of length L moves with a constant speed V. Wire making an angle beta with the vertical direction. Well, it looks like a theta in my picture, so this should be a beta. Find the tension F in the wire and the period T. Now, the period for a pendulum. We haven't really talked about that, have we? We need to talk about what is the period of a pendulum. Or do we? Let's go back to the very beginning of what we know. First thing we need to find is what? Tension F in the wire. So let's start with F. Okay? So for tension F, is equal to what? All right, force of tension. I just wrote that backwards. So for the tension in the wire, what do we know? We know that we're using it ML, beta, and G. So we know that it's got a centripetal force or an acceleration, centripetal going inwards, okay? We know the radius, or we should be able to find the radius. So radius R, from the previous problem, you will know that the radius R is going to be L, what? Sine beta. Okay? It's going to be L sine beta. All right. So now, for the tension, we know that what? We know that the sum of forces centripetal is going to be equal to, oh, I'm going to do it that way. Forces that we have is we know we have mg down, and we have tension force this way. So I'm going to do the same thing again. Break this into two pieces. Beta is up here, so this becomes F sub t cosine theta, or cosine beta, excuse me. So I know that for the tension force, I'm going to use the components here and here. I know those have to be equal and opposite. So the force of tension has to be equal to, well, force of tension cosine beta has to be equal to mg. So the force of tension is equal to mg divided by the cosine of beta. Okay, got that. So now, part B, let's find the period. Find the period. What do we need to do? Well, what would the period be? We have something going in a circle. Let's go all the way back to what we were talking about earlier at the very beginning. We said if we knew what the speed was, we could take this speed 2 pi r. So the velocity would be equal to 2 pi r divided by the period. So the period instead is going to be 2 pi r divided by the velocity. So what we need to do is we need to find r, which we know, and we need to find the velocity. Well, to find the velocity, we're going to use a sub c. So sum of forces centripetal is equal to m a sub c. That is going to be mv squared over r equal to what? F sub t sine beta. So this is equal to F sub t sine beta. Well, we know what F sub t is, so let's plug that in. mv squared over r is equal to mg sine beta over cosine beta, because that's mg cosine beta. I put it that way because I want to put this together. M goes away, so we're left with v squared equaling rg tan beta. So now we just have to take the square root of both sides. So we have V. So let's plug this in. Plug it in up here. So we have T equals 2 pi R, we said was L sine beta, divided by V, square root of RG tan beta. So I would like to put all the betas and everything. We could leave it like that, but it's kind of ugly. So if I want to put everything up underneath, I'm just going to leave it, quite frankly. I wouldn't work it any further than that, guys. You can get it to this, you can get it to that, but it's a pain. And you don't have to. All right, guys. So pretty much the last example, because the next one is just another example of this, but conceptually, so I'm going to do it all in one. If you look at this, we have a banked curve. That means it is at a curve like on a racetrack right here, which means it changes everything around. So we have mg going straight down right here, okay, but we have the normal force off at an angle, which means that we're going to have to break it into its component portions here and here. This, of course, is going to be the normal force times the sine of theta, and this is going to be the normal force times the cosine of theta. Well, to figure out what the normal force is, because this chunk of it right here, this chunk is the portion that is going to be in the x direction, which is for your centripetal. So the force centripetal, which is going to be ma centripetal, is just going to be the normal force times the sine of theta. Problem is we don't know what the normal force is. The normal force is not mg this time. The normal force cosine theta is mg. So we have to come over here and find that first. What is the normal force? So the normal force is equal to, times the cosine, of theta, is equal to mg. That means that the normal force itself is mg over the cosine of theta. Okay, so we're going to take that and plug it in right here. So we have mv squared over r, because centripetal, v squared over r, is equal to mg sine theta over cosine theta. So this itself goes together. M goes away. The max, there's no friction. So we've got v squared over here equaling rg tan theta. So the velocity is going to be square root of rg tan theta. Okay, so we can plug in values there. Radius is 65, gravity's 10, times the tangent of 20 degrees. We should get approximately 15.4 meters per second that this thing can go, that's as fast as it can go without needing the assistance from friction. All right. So now if you take this guy, it says car goes around with no assistance from friction. If it's moving v, what angle should the curve be banked? Well, we know from the previous example, if you think about that, the velocity is equal to the square root of rg tan theta. So we just go back to v squared equals rg tan theta and solve for theta. So we have v squared over rg equals tan theta. So theta is just going to be equal to the inverse tangent of the velocity squared times divided by rg. All right, and that's all there is to that. So we are ending uniform centripetal motion. You've seen systems as well. You need to be working on your homework and getting it done. We have one more day of advanced problem solving before we review for the last test, and we're done.